Okay, so today is the second, oh, I feel very, very short all of a sudden. Today is the second part of our concrete lecture. But before we can talk about concrete, we need to talk about composite action. So there's something really interesting happening with concrete, actually at two levels. We have a bunch of rock and sand that we mix together and make them act as one thing. And we have steel embedded inside that, also helping make it act as one thing. And so the key there is what makes it act together, and that is composite action. So we're going to talk a little bit about load sharing. So if we have something in compression, how does it load share? So how much of the load goes to what part, and how we would calculate that. And then we're going to talk about that same concept, but in bending. And we're going to look at what happens if we just share the load versus bind those two things together in a way that makes them composite. And then I'll go on and talk about actual design with concrete columns and beams. I think you guys have done a lot of work so far this term, so you guys aren't going to be responsible for actually calculating concrete in bending and compression. But I am going to talk about the mechanisms within the element that resist the loads and how it works, and I expect you to know that. So load sharing is when two elements or materials are arranged so that they mutually support the load, and they are said to be sharing the load. The proportion of the load that The portion of the load that each resists is proportional to the stiffness of that element or material. Load will follow the path of greatest resistance, or the stiffest element. So, that old adage, follow the path of least resistance, that is bullshit. The load is going to go to the stiffer element. It is going to follow the path of stiffness. It is going to be attracted to the stiffness. So multiple elements supporting the same load share it based on stiffness. But also embedded within that, we know that if you have a big thing and a small thing, the bigger thing is going to carry more load. So we have two things we have to think about there. We have to think about area, and we have to think about stiffness. And so it's some combination of those two things that actually helps carry the load, or a proportion thereof that carries the load. So how would a concrete and steel column share load if they were embedded together or working together? Kid just half climbed a window and then fell down. To share load at all, they need to move together or squash together. Let me get out my trusty foam block, which is hiding at the bottom. Oops. Keep it away from my kids. All right. So, for this to share load, it has to move together. If the load's only here, you can see only this side moves, and it would take all the load. So to move together, they must be moving together. If they're moving together, is he okay? What's he doing?
He's in his box.
Is he in the costume box?
No.
He didn't fall, he climbed in a box. Is he laying down? Is he playing? Is he just laying there?
He's just laying there.
What a kook. It's the 2-year-old.
He's hiding from Dad.
He's playing hide and seek. Friend, kids are cute. Oh my god. Sorry. Heart swelling, can't stop it. So, what do we know about things moving? Well, we know that measurement of how much it moves compared to its original length is strain. So if those two things are moving together or having the same amount of delta, we know that they must have the same strain. So there's a relationship there that means we can start to calculate things. So if we remember our basic formulas going way back early in the term for you guys, Stress was force divided by area, or you could rewrite that as force equals stress times area, or this right here. We know that strain is delta L divided by L, and we know that E, or the modulus of elasticity, is stress divided by strain. Or we could say stress equals E times strain, or modulus of elasticity times strain. And we know E is representative of stiffness. So we know that if there's two things sharing this load and they're moving together, they have the same strain, but they might have different stiffnesses. The two different materials might have different E values. So just using these equations, we can start to substitute things into each other. So force equals stress times area, or force equals E strain A, or E strain A, where E and A are for each material. So they have different modulus of elasticities and different areas. But the strain is going to stay the same because, it's going to be the same strain because they're moving together. So for each material, so if we had a steel and concrete element sharing load, the force in the steel would be the modulus of elasticity and the area times the area of the steel times the strain, which is the same for both. And the force in the concrete would be the modulus of elasticity of the concrete times the area of the concrete times the strain, which is the same for both. But we want to relate this to the total load. Well, the total load is the force in the steel plus the force in the concrete. That has to be the total load because that's all the load. So F equals the force in the steel plus the force in the concrete. Well, we know the force in the steel was EA of steel times the strain, which is the same strain, or EA plus EA of the concrete times the strain, which is the same for both. Let's pull strain outside of that, just because we know we can take, if it's multiplied, if both things are multiplied by it, we can bring it outside and put a bracket around it. So the strain, which is the same for both, times the sum of the EAs, or the sum of each EA of each material. If there was 5 materials, there might be 5 EAs all added up. So the sum of EA is the axial stiffness of the combined or the total system. If we wanted to rearrange that, the strain is the force divided by, your phone is down here, Dave. Force equals the sum of EA. Well, I just figured you might need it for your call.
I'm on my computer, but...
Oh, sorry. Sometimes you need to switch back and forth, so I thought you might find it super helpful. It's not just about annoying me.
Yeah.
I did hear you say that to whoever you're in the meeting with. So this strain, which is the same across the board, is equal to the total force divided by the sum of the EA. Well, if we know that the force in the steel is equal to the EA of the steel times the strain, well then that means the force in the steel is equal to the total force times the EA of the steel divided by the total EA, or the ratio of the stiffness of steel to the stiffness of the whole system. And this is a concept we do with resistors, we do it with all kinds of things, where this is the ratio of the stiffness of one part versus the total part. And then that is just the total force. But we determine this with that basic principle that they must be moving together. So let's take a look at an example now. Okay, so we have a column that is a square HSS column filled with concrete. And we want to know what percentage of the load goes to the concrete and what percentage of the load goes to the steel. You know, I always tell you to take a guess at the beginning before doing any calculations. What does your intuition tell you? Well, looking at area for this column, it looks like there's a lot more area of concrete than there is steel. My gut is telling me more is going to the concrete than the steel, but I know that load also goes to the stiffer element. If this was filled with bubble gum and this was steel, and they both moved together, some load would go to the bubble gum, but most of it would get carried by the steel. So more load would go to the steel. So it's not just about area, it's also about stiffness. And I know that steel is much stiffer than concrete. So that throws off what my intuition is going to be. But what I can figure out is that it's not clear to me. So it's, I'm going to say ballpark, 40-60 to 60-40. So somewhere in that range. I'm not quite sure, but the steel could take anywhere from 40 to 60% is my guess. That's my baseline gut number, but nothing is coming from that, just simply my gut feel. They've told us that the modulus of elasticity, or the stiffness of the concrete, is 30,000 MPa. So let's start this calculation. I'm going to make my screen bigger here, and I will grab my pens. So the first thing we need to know is we need to know what the area and the stiffness is for both materials. So we know that, or what we don't know, we need to look up the area of the steel. Now, where could we find the area of the steel? They said it was an HSS 152 by 152 by 9.5. Well, we know that we have steel properties for different members. So we can go to that steel properties table, the steel member properties, and look up what the area of this steel HSS is. And we can look it up, and it is 5,210 millimeters squared. So we've looked that up, and we know that that's the exact area of that steel member. We know that the E of steel is 200,000 MPa. I've told you that quite a few times, and I said it's one of the few things I want you to remember. And then let's just, because we know we might need it, what's the EA of steel? Or our E times A. We've got 200,000 times 5,210. That is in MPa, or newtons per millimeter squared, and that is in millimeters squared. So let's plug this into our calculator, or 200,000 times 5,210. We get, that looks like a really big number, but look, I'm going to go 3, 6, 9, I'm going to go 1.042 times 10 to the 9, because I don't feel like writing all of those zeros. And that was newtons per millimeter squared times millimeters squared, so leaving me an answer in newtons. Let's do the same thing for the concrete. Let's figure out the area of the concrete. Well, interesting. I realized I just could have done. Anyway, so the area of the concrete, well, we know that it's pretty darn close to a 152 by 152 square. So something like this, but we know that there's some amount at the perimeter that's actually steel, and what we want is that bit in the middle that's concrete. So we actually want this bit in here. So what if, so we want that times that. I'm not going to worry too much about the rounded corners in there. Well, this total dimension was 152, and that total dimension was 152. One of the great things about HSSs is the information for how thick this piece of steel is right in the name of it. So all of these are 9.5 millimeters. So the area of the concrete is 152 minus 9.5 times 2 times 152 minus 9.5 times 2, or 152 minus 9.5 minus 9.5 times 152 minus 9.5 minus 9.5. Let's calculate that out. We've got 152 minus 9.5 times 2 times 152 minus 9.5 times 2. We have 17,689 millimeters squared. So a much higher area than the concrete. In fact, it looks like just over 3 times the area of concrete. But the E of concrete, they gave us right in the question. They said it was 30,000 MPa, which is, this is almost 7 times as big. So as much as the area of the concrete is 3 times as big, the stiffness of the steel is 7 times as big. I'm going to revise my guess. I'm going to guess that maybe more load goes to the steel. I'm going to change that revision. I don't know how much, but I think I'm closer to the steel taking more load now. Just because the stiffness of the steel is greater than the area of the concrete is greater than the steel. All right, so let's figure out what the EA of the concrete is. We have 17,689 times 30,000 MPa. That's a pain. I wrote it backwards compared to what I did for this one. You guys get the idea. Maybe I'll just write E steel, area conc, E of the concrete. If we plug that in, 17,689 times 30,000 MPa. Yeah, it's a big number, but look at that. It is only 0.5307 times 10 to the 9 newtons. So it looks like the combined EA of steel is greater than the combined EA of concrete. Well, we want to know what ratio of that total EA is steel. So let's look at the sum of the EAs. So that's going to be the EA of steel plus the EA of concrete, or 1.042 times 10 to the 9 plus 5.307 times 10 to the 9. The EA, the sum of the EAs plus 0.5307. I end up with 2, 3, 4, 5, 6, 7, 8, 9. 1.93. Oh, look at that. Made a typo in my calculator. Perfect. 0.4. That's better. 1.042 times 10 to the 9 plus 0.5307 times 10 to the 9 equals 1.573 times 10 to the 9 newtons. Well, we want to know the force in the steel, and we know the force in the steel is the force times EA of steel divided by the sum of the EAs. Well, we don't have a force. We want to know what percentage of force, so we'll keep force as an unknown, times the EA of steel, which was 1.042 times 10 to the 9 newtons, divided by 1.573 times 10 to the 9 newtons. We get 0.662 F, or 66.2% of the load goes to the steel. Now, for those of you who really have a feel for this, if 66.2% goes to the steel, well, somewhere around 34% must go to the concrete because it has to sum up to 100%. But let's just double check that. Let's look at the force in the concrete. The total force times the EA of concrete divided by the sum of the EAs equals force times the EA of our concrete is 0.5307 times 10 to the 9 newtons divided by 1.573 times 10 to the 9 newtons. 0.5307 divided by 1.573. We get, well, there's a bit of a rounding error there, but 0.337 F, or 33.7%. So that sums up to 99.9, but you know, that's a small rounding error in the calculation, which is well within acceptable norms. So we can see that 62% of the load is going to go to the steel, and 34% is going to go to the concrete. And that wasn't totally obvious just looking at this. You had to have a feel for how stiff each part was, but we have that calculation. So now if we knew how much load this was carrying, we could say how much load is in the steel and how much is in the concrete, and then we could check if that HSS is actually strong enough to carry that load. So there's another part to this I want to talk about. So here that is all worked out. One of the things we can do is, because this is kind of hard to just see at a glance. We talked about the area and we talked about the stiffness. One of the things we'll do is we'll transform the section, or we will pretend they're both the same material. So instead of having different EAs, we'll figure out what the total EA is and talk about them both as if they were the same material. Or how much steel would it take, or how much concrete would it take to be the equivalent amount of steel? Or if we had, in this example, the EA of steel is 1.042, what equivalent amount of concrete would that be if it was 30,000 MPa concrete? So how much concrete would that steel be equivalent to? So, again, our strains are the same. So any object of any material or combo of materials will act the same as long as the stress EA is the same. So we can talk about them in terms of each other. So the transformed section is really talking about that ratio. And we'll often do it as an area, or the transformed area. And often what we do is we transform the steel into concrete. And you're going to see later in this lecture why that is so handy when we talk about concrete beams in bending. So let's take a look at that HSS column that was filled with concrete. We want to transform the steel into an equivalent column of concrete. So if that was actually all the same thing, what would that look like? Now, we've already figured out the area. Let's make this bigger now. We already have the area of our steel and the E of our steel, and the area of the concrete and the E of our concrete. We want to know what the transformed section is, or area transformed is the E of the concrete divided by the E of the steel times the area of the steel. Or what we're saying is, if we pretended this steel was concrete, how much would we need it to be? So we have 30,000 MPa. Look at me, I'm writing things backwards today. Sorry guys. That immediately didn't seem right as soon as I started to write it down, because it's going to be bigger. Because our steel was so much stiffer than our concrete, our area is going to end up being bigger if we talk about it as if it was the same stiffness. So we're pretending that they both have the same stiffness, so the area of the steel must get bigger. So the transformed section, the E of the steel divided by the E of the concrete, or remember that's about 7 times, and then we're going to change that into a transformed area of steel. 200,000 divided by 30,000 times that area of steel that we had. We can plug that in here. 200,000 divided by 30,000, so 6.667 times the stiffness, times 5,210, 34,733 millimeters squared. So if we wanted to talk about this as if both things had the same stiffness, we would have to change this thing that is actually stiffer and pretend it is a thing with these dimensions. So that is the area, or the transformed area, 34,733, and that is the area of the original concrete, which was 17,689. All of a sudden, it's really easy to see that more of the load is going to go to the steel. It's now very easy to see that equivalent. And the total area now would be, so the concrete column, so this steel wrapped column is the same as a column with 34,733 plus 17,689 millimeters. Let's plug that in. 34,733 plus 17,689, 5,000, so 52,422 millimeters squared. So this concrete with an HSS wrapped around it is the equivalent to a concrete column that has 52,422 millimeters squared of area. It lets us talk about it in a slightly easier manner. So that means we could start to try to solve this problem in a slightly different way. But We know that there's a buckling thing, and so it's not really exactly true, but it gives us a place to start our conversation. So that's how we look at stiffness load paths in columns that are load sharing, and how we transform the area of one material into the other, or pretend that one material is the other material, and what that equivalent area might look like. And you can see that worked out here. Okay, now let's talk about composite systems. So we've looked at load sharing, and within that we talked about stiffness, and we talked about transformed sections, or talking about one of the materials in terms of the other. We're basically pretending they're both the same material, and talk about their area in terms of their stiffness, or you could do it the other way around. Now let's talk about composite systems. So if two systems or materials are combined so that they support load as one, the system is said to be composite. In order for a system to be considered composite, the materials must be bonded so that they won't slip relative to each other. So in axial loading, that's easy. We can just glue them together, or it's just load sharing. It doesn't really make that much of a difference. But in bending, we need to make sure shear can be transferred across the plane where the materials interface. So that act of shear, or actually this act of shearing, so not shearing in this plane, but shearing in this plane, we need to make sure the things won't slip relative to each other. So it could be two different materials, or it could be something like glulam beams. So, composite versus non-composite, or load sharing. For bending elements, longitudinal shear is critical. If there is no bond along the interface, or the shear plane, the elements will slip along that plane. It's like two small beams sharing load. If we can ensure there isn't slip, we have one deep beam. And a good way to think about it is trying to bend this paper. If I do this, if you look up close, it gets a bit fuzzy, do you see that all of those pieces of paper, they've slipped relative to each other? And then when I go back, they're in line. So they're in line right there, but look, they're not in line anymore. That is because there is longitudinal slip, or they are shearing relative to each other. If you took those pages and put a thin layer of glue between them all and bonded them together and tried to bend it, you would have something much, much stiffer. If you think back to plywood, that is exactly what we do with plywood and glulam beams. So let's look at two 140 by 140 timber beams spanning some unknown distance. So now we want to look at bending for composite versus non-composite. In fact, maybe we'll even do it in compression as well. We want to go through and look at what making something composite does to its capacity. So, if we have a 140 by 140 beam glued onto or sitting on another 140 by 140 beam. So both of these are 140 by 140, and here's its length of some distance. If it was non-composite, you'd see it slips along this longitudinal shear plane. And so this is the maximum stress, maximum stress, maximum stress, maximum stress. We have two beams stacked on top of each other that would both yield when the extreme fibers hit their maximum stress. If we glued them together, they're forced to act as one big element. So the maximum stress would be here and here, not in the middle. So we've increased the depth of this. Let's take a look at what that means. Let's do it by calculations. So let's take a look at shape properties. If you guys remember, axial loads, so compression, and shear loads both used cross-sectional area. Bending used the section modulus, and stiffness used a shape property called I, or moment of inertia. Let's take a look at how making it composite versus load sharing affects that beam for all of those conditions. So let's draw ourselves this section. We've got two different versions of it. We've got it like this, where they're just stacked on top of each other. And we've got it like this where we know it's two separate sections, but we've glued it together in a way that we're making it act like one big section. We've forced this to act as one big section. So its stress profile, it hits its maximum stress top and bottom. So let's take a look at axial and shear, which use area as the shape property. So let's do a sharing. We have two 140 by 140 members. So we have 140 times 140 plus 140 times 140. We multiply that out. Let's take a look. We've got 140 times 140 plus 140 times 140. We've got 39,200 millimeters squared. Let's just write this out. We've got 140 140 and 140. This is 140 wide. And because we've bonded these together, we've effectively made that 280 millimeters deep. So that's our load sharing. Let's see what it does, area for making it composite. We have 140 by 280 equals, let's do 140 by 280, 39,200 millimeters. Well, you're probably thinking, well, that was boring, Shannon. That didn't do anything to our system. It looks like A sharing equals A composite. Let's talk about S, which we use for moment. You guys remember, for a rectangle, S equaled BD squared divided by 6. So let's take a look at that. Let's take a look at S sharing. We have 140 times 140 squared, or B times D squared divided by 6, plus 140 times 140 squared divided by 6. So 140 by 140 squared divided by 6 plus 140 by 140 squared divided by 6. We get 0.915 times 10 to the 6 millimeters cubed. Let's take a look at it in composite. So S. So remember, we've effectively made it 280 deep. So we have 140 by 280 squared divided by 6. So 140 by 280 squared divided by 6. Ooh, this looks like it's a bigger number. We have 1.83 times 10 to the 6 millimeters cubed. It looks like a composite is 2 times the area of sharing. So making it, S, that's supposed to be S. By making it composite, we've increased S, or our section modulus, which is just a shape property of our element, but we know that this is used to calculate bending. So if we've doubled S by making it composite, that means we've doubled the capacity. Let's take a look at stiffness. Stiffness, we used I, or moment of inertia, for stiffness. And if you guys remember, I'm just going to put this here. BD squared divided by 6. And this is BD cubed divided by 12. We didn't calculate this, but I did show it to you in a lecture slide. So let's see what it means for I sharing. The I for sharing is 140 times 140 cubed divided by 12 plus 140 times 140 cubed divided by 12 equals 140 times 140 cubed divided by 12 plus 140 times 140 cubed divided by 12 equals, 1, 2, 3, 4, 5, 6. It equals 64.0 times 10 to the 10 to the 1, 2, 3, 4, 5, 6, 10 to the 6 millimeters to the 4th. Let's take a look at I composite. $140 times 280 cubed divided by 12. 140 times 280 cubed divided by 12. We have 256.1 times 10 to the 6 millimeters to the 4th. Or by making it composite, I composite equals 4 times I sharing. Making it composite, it is 4 times as stiff as having it load share. So that simple act of providing a bond there makes it 4 times as effective for stiffness. So our glue-lam beams, which really are a series of 2x elements, the reason just stacking them on top of each other isn't enough, we need to actually glue laminate them together so that we get that composite action. So you can see that again, all worked out right here without any of the typos as I go along, which I've corrected as I did it, but here it is all worked out. again. Okay, so what are some famous composite systems, or where do we really benefit from this process? So one of the most common ones we use is composite concrete on metal deck. We often just call it concrete on metal deck. And we looked at this when we talked about our steel component. We often use it in steel buildings, but you see these little bumps right here that we have sticking out of the deck? Well, that is when we just use the deck all by itself. We didn't have those. What those do is they just bump in and grab the concrete just a little bit. So when the concrete cures around it, if you try to bend it, they can't slip relative to each other because there's that bump there. We know that steel is great in tension and concrete is great in compression. And remember, for things in bending, we've got compression at the top and tension in bending, or tension at the bottom. So we have our steel where the tension is the highest and the concrete where the compression is the highest. And so we've made a great composite system by making use of both elements. The rebar in concrete on metal deck actually isn't doing much structurally. If you had a deep enough system, maybe it would do something, but mostly it's about crack control. Concrete, when it cures, shrinks, and it will crack. It always cracks. And I forget what the ratio is, but like something like a millimeter, a meter, maybe a bit more than that. So over that meter, you could get one big crack, or you could force it to have a series of smaller cracks. So you can take the paint all at once in one big crack, or you can have a series of smaller cracks. In other concrete, if we do saw cuts, we'll actually try to force where those cracks happen. It doesn't always work, but we try to. But that's a talk for later. If we actually punch steel studs down into our steel beam, and I talked about this when we looked at steel systems, you can actually make use of a little bit of the concrete on metal deck as the top of the beam. So instead of a beam just being this deep, we get to use a little bit of the deck and concrete as well. So we make something just a little bit deeper. So the concrete is doing the compression, the bottom of the steel is doing the tension, and then there's shear transfer because we've bonded this concrete around the Nelson stud, so it kind of gets cast around it and grabs onto it, and then that gets welded onto the steel. When we were talking about wood systems, you remember when I talked about the case system, or the class system, whether it was class 1, class 2, or no class at all. No class meant that it was just acting on its own. So if there was no plywood on here and you stood on just this joist all by itself, it was doing all the work on its own. And I explained how, if we're standing on this, it's trying to drag the plywood down with it. Well, really what we're saying is we've got a little bit of a composite system. This plywood is acting like a top flange on this joist here. So as the joist tries to bend, it's bracing it, so it's increasing its capacity, but it's also trying to bend the plywood. And if it's nailed together and glued properly, you can't have those two things pop up relative to each other, and you've got a composite system. Engineered I-joists. Well, the web itself is all glued together, little bits of wood or oriented strand board, OSB, and so that's composite. And then the fact that it is notched and glued into these top and bottom cords, that right there is also transferring longitudinal shear, or forcing these to be composite. It is not a beam up here and a beam up here that are sharing load. It is one entire unit acting together. SIPs, or structural insulated panels. Not that common, great for prefab construction where you have insulation built into your system. Well, the insulation is glued to the top and bottom board, and instead of just two pieces of plywood, you've got two pieces of plywood with some depth in between them, so increasing the effective strength of that system. And then you can have advanced composite systems. So concrete, for example, we will take kind of fiber pieces and glue them onto things. So those fibers can be glass or Kevlar or carbon strips. The idea here, so you'd wonder, well, why wouldn't we just build the whole thing out of this? Well, one, it's really expensive. Two, it has no compressive strength whatsoever. It's because we're laminating it onto the concrete that it has strength. And so why wouldn't you just do it on concrete right away? Like I said, it's really expensive. So where we use this is often in remediation work. So if our concrete is starting to spall off the bottom, we might put those strips on the bottom of it to adhere it on and work as a tension base on the system. But the big important one that we want to talk about today is concrete. So reinforced concrete is a composite system. The elements within this do different jobs. If it is compression, so we're squashing it like this, there is load sharing happening. Even if it was composite, even though it is composite, it doesn't matter because it's just going to share the load based on its cross-sectional area and its stiffness. We actually often don't count on these pieces of steel rebar. As much as they're there, we don't often count on them. Sometimes we do, sometimes we don't, but mostly we'll just count on the cross-sectional area of the concrete. Tension? Well, in tension, we use our steel. So especially if we're talking about bending. And in shear, we actually use these ties and we use the cross-sectional area of the concrete. So I showed you these slides last week, these few. I'm just going to refresh your memory. The Fy of our rebar is 400 MPa, and you guys remember that the E of steel is 200,000 MPa. That's just something I expect you to know. And then the various sizes of rebar, we talk about them in M, which is approximately the diameter of the element. So a 15 M bar is about 15 millimeters in diameter, so if it's that much around. And so here are the assumed areas that we'll often take into account when we're designing in concrete. 10 M bars are really floppy. They bend if you step on them. So because of that, we don't like to use them as the main structural element. We will use them for shear reinforcing for our ties or for crack control on things, but not anything that we're often laying out in a grid that you might need to walk around the site. You guys saw last week what the slabs look like with the reinforcing mesh, or all of that mesh of reinforcing in it. And it's hard not to step on those bars. So we often space them as low as 2.5 times the diameter of the bar, and we might go up as high as 500 millimeters, or 3 times the thickness of the wall or slab. And the reason that is, so if we have a wall here, and I'm going to draw some bars like this. This is the cross section of a wall. You can see I've got rebars in plan, so this is looking down at a wall. But the bars can only be so long, or maybe we're doweling out of our footing, and there's a certain spot where they need to lap. So we actually have, at certain spots, what looks like 2 bars side by side for some distance or some length, or what we call our lap length. So there'd be some distance that we lap there. And so we still need to be able to get concrete in between them. So if they're too close together, if the bars are too close together, we can't lap and also get concrete in between the bars that are working some distance apart. Fewer larger bars is cheaper, but more smaller bars work better. We tend to stick for structural components in the 15 to 20 M range, and then we bump into 25 to 30. Getting bigger than that actually starts to be very expensive. 45 and 55s are available, but we actually can't lap them. We have to have couplers that actually join them together. So they're quite expensive and quite difficult to work with. You would use those on kind of very large scale concrete buildings. Just some general ideas of concrete strengths. So footings and caissons might be 20 MPa. Remember, our steel was 350 MPa, and our wood varied between 8 and 15, depending on what job it was doing, what grade it was, all of those different factors that we looked at with wood. So footings and caissons, 20 MPa. A high-rise column might go up as high as 70 MPa, but there's a real cost premium once you kind of get up into that range. But 20 to 30, not that much of a difference. The mix designer will look at what our requirements are and then come up with a mix design that talks about the water to cement ratio and the air entrainment, where those are the tiny little bubbles that are in it. So let's look at two stress strain curves. So here is the concrete by itself. It's got 0.65 as a reduction factor, or remember, we need our reduced capacity to be greater than our factored load. So our reduction factor on concrete is 0.65. Our reduction factor on rebar, or reinforcing steel, is 0.85. Regular steel was 0.9. Wood changed depending on if it was in bending or compression, but it was 0.8 or 0.9. But concrete has a very low reduction factor. So whatever we calculate, we only take 65% of it. So a concrete column in compression. Concrete and steel share the load based on stiffness. So that's the area and the material stiffness. The steel does two things. If it's a big enough column, our quick check, we might just look at the cross-sectional area of concrete, because that might just give us what we need. We'll put steel in it still, but we'll often just look at the concrete first as a quick check. The longitudinal steel carries load, as you saw when we had the concrete in a steel HSS. It's the same concept. But we also put ties around that reinforcing to keep the concrete from bursting apart. So that lets it reach its full compressive strength. And that is based on column geometry. So there's not a lot of engineering to that. That is literally pulled out of tables that talk about column geometry. So the reason concrete columns are neat in compression is the column is composite, so the strain must be the same for steel and concrete, and we talked about that. Steel is way stiffer than concrete. The steel stress will be much higher than the concrete stress, even though they have the same strain, because we know that it will attract more load. The steel yields before the concrete reaches its full stress capacity. So the steel starts to yield, but it doesn't fail. When steel yields, it doesn't fail. It's ductile. So it will just deform some until the concrete then reaches its full capacity. So based on the fact that the steel is ductile, we actually end up getting to make full use of both materials. So what do concrete columns look like? So I found this chart. It was a British chart, so the nomenclature is a little bit different than what we look at. But this looks like a very normal column. So most of the time we'd have something that looks like this. But you can see for a square column, we always make sure we have bars in the corner. And depending on how much steel area we need, we might add more reinforcing. And then this bit that goes around, that's the ties. That's the part that keeps it from bursting. And look, you can see the ties right here. And they have to be closed. They actually have to loop around onto themselves. Now there's different ways you can do that. You can actually have this be one piece that hooks here and comes around like that. That's hard sometimes. Sometimes what they'll do is make two U's and put them together like that. As you get into larger columns or more complex columns, honestly, I've never done any of these. I've never seen one that looks like that, but I have done, this is probably 95% of columns looks like this. Round columns, if you're doing maybe a sonotube, for example, or a caisson, would often be round, or you might do a building with a round column. Again, we have closed ties. They might spiral the ties, so it goes around like that, with the spacing between the spiral being the spacing that we would have called up in these ties. You can have funky shapes in your columns as well, but we just have to make sure we've closed this in some way that encloses our loads to stop the concrete from popping out. When I was in my concrete course, we hadn't talked a lot about this, and our teacher gave us a question that made it seem that we had to do all kinds of complex work. It was worth 40% of our mark, and he said, design the reinforcing for this column. And there were tears. There was lots of people crying. People didn't know what to do. And what he was really looking for, actually, that's not even a good version of it. I'm going to draw it less. He wanted us to draw something that had closed elements. So a circle around our primary steel, and then something that closed off those elements out there. All he wanted was a drawing. There was no calculations required, and there were a lot of tears for that. I wish I had seen this slide before he asked that question. So now let's talk about concrete beams and bending, because it's really kind of cool. There's lots of things happening that are really cool here. I fixed this slide, I thought, last year. So I'm going to fix this slide for you guys. So I'm going to show all the slides. Slide 29, the order. So don't worry about this. Let me bring everything up. Those were supposed to come in counter to each other. So, and I'll color code it as well. The compression zone. The concrete does all the work in the top part, or the compression zone. We can add those pieces of steel in if we want. We don't that often. We might if we're really pressed. The steel does the work at the bottom, or the tension zone. So remember, if we're bending like this, the top is in compression and the bottom is in tension. Steel is good in tension, concrete is good in compression. So we're making use of the concrete at the top where it's in compression and the steel at the bottom where it's in tension. So the best of both materials. Remember that transformed section property I talked about? Well, what we do is we pretend that steel is actually concrete to be able to talk about it as if there was a blob at the top and a blob at the bottom. This is our strain diagram. It must be deforming the same at the top as it is at the bottom. So somewhere right along here is what the strain looks like at the rebar level. And this is the stress in the concrete portion, and right here is where the concrete would fail, where the extreme fiber of our brittle material would, if FC hits our F prime C, or that maximum value of compressive strength for our concrete, it fails, and this is the stress in this portion, which we've represented as actually the force in the steel, which is a ratio of its area, or its stress related to its area. And this is an idealized curve of what the concrete looks like to figure out where the center of that is. And so what we really have is a stress-strain distribution that looks like this. And we have our stress block at the bottom in tension is represented as an arrow. And our stress block for the concrete up here is represented as a block. Don't worry about beta and alpha, they're about properties of the concrete. If you stick with me and join the master's program, you will go through my Structures 2 course where we actually break this down and do these calculations. I think it's too much to ask of you guys to do in one lecture, and it's also the end of the term and you're exhausted, and I think we've done a lot. So I'm just going to show you what this stress block looks like, or the cross-sectional stress profile of a reinforced concrete beam. This makes a good exam question. So that you can see that the compression's all up here in the concrete and the tension's all down here in the steel. So what's happening with a concrete beam in shear? Well, in shear, these ties are doing all the work. And the cross-sectional area of the concrete is doing all the work. So we have two parts. What we often do is a quick check of the concrete, and if it works, same thing as compression, no problem, it's good. But if that's not enough, we'll add in the stirrups. We often have the stirrups even if we don't design them, just because it helps for crack control as well. But that might then make the equation more complex and actually bring them into our calculation. So remember our concrete when it failed, when that very first lecture, and I showed you concrete failure, as we tried to slip two things past each other, if we moved them farther and farther apart, or we kept slipping things relative to each other, we'd start to end up with something that looked like this, and we'd skew our square. Well, that skewing is really elongating our top and bottom points. And so our cracks actually follow along that path because it's concrete and it doesn't like tension. So we'll actually get cracking in this diagonal pattern. And we put these shear stirrups across the path of the cracking. So it hits a steel stirrup and stops cracking. So you can see here, that's a shear crack starting to form in a beam and bending, and it hits this stirrup and helps prevent the cracking. It's really like modeling this as if it was a truss. We pretend our steel is acting like a truss within this element. Again, I'm not making you do any math. I want you to know that the shear in a concrete beam is carried by the concrete and the steel ties. So what do concrete beams look like? Mostly they look like this, or this one right here. This would be the majority of concrete beams. Most of our steel is down here at the bottom. If we have a beam that reverses direction, we will add steel up here as well. And this is an interesting thing about concrete. Concrete, because of its size, inherently has moment connections. And that means, I'm going to get a better piece of paper here. And that means that if we had a steel system that looked like that, and a concrete system that looked like that, you can see I've closed the gaps. That's implying that they're all connected together. Our bending moment diagrams for our steel would all look like that. We've looked at that, we've designed that. So that is a simply supported beam in bending. That's the moment diagram for it. Our concrete one, look, we've got positive moment up here and negative moment down here. So that means In the middle, our bending is like this, but over the columns, our bending is like this. It's almost like the column is acting like a prop and making it bend in that direction. So in that condition, our tension is at the top and our compression is at the bottom. So we might need top steel up there. Often, if this was a beam, we would often design it so that we have continuous bottom steel, and we might only have top steel where we needed it designed for the reverse bending. You can see that if it's really working hard, we might need 2 layers of steel down here. You can imagine that makes that stress profile diagram look a little more complicated, because now the arrow is somewhere in the middle of those, or the centroid of our tension elements. And you can see we've got our ties in here that are helping prevent shear cracks from forming, or failure in shear. It's also helping with crack control. This beam right here is what we might do if it was actually embedded in the slab. So we can do 2 things. Actually, we can do 3 different things. If this was a beam and maybe this is a beam, depending on the amount of load in it, we might be able to actually fit our steel in the depth of that. Remember I said I hate the width requirement or the width sizing guideline for concrete? This is why, because sometimes if we can make it work, we'll make it wide enough to fit in all our reinforcing as long as our depth works. We can actually also, and that is this drawing right here, we can actually make use of the fact that we're tied into our slab there by actually making some of the slab even more part of our beam, or a T-beam like that. So you can really work with concrete to take advantage of whatever you need depending on where you put your steel. But you need reinforcing steel where you have tension, you need concrete where you have compression, and you need steel and concrete where you have shear. So some takeaway tips. Load follows the stiffest path. Load sharing of 2 members is additive. Composite action of 2 members acts like one big member. Longitudinal shear is required for that composite action in bending. Compression, steel and concrete. Bending, concrete for compression, steel for tension, both for shear. So that wraps up our composite lecture and our concrete lecture. Next week, we're going to talk about lateral load resisting systems and foundations to wrap up the term. So see you guys. Also the course evaluations, you guys should have gotten announcements for that. Take the time to fill them out. They're obviously anonymous. I do get to see any comments you guys write. It doesn't tell me who wrote them, and I don't even see them until later in the term. You can say whatever you want. You can say you hate the course. That's totally fine. That is your prerogative. But what helps is if you give feedback. Like, I hated the course because here's what you could do better is obviously going to be the only way I can make it better. Some things I can't help with. If it's I hate the course because I hate math, I hear you, I get it, but we can't take the math out of the course. If it's I hate the course because Shannon has a high squeaky voice, not much I can do about that either. But if there is something that I can possibly do about the course and other people agree, I will try to implement it. I've tried to implement those things throughout the term. Somebody gave feedback about the size of the mouse pointer, so I found a way to make the mouse pointer bigger. I am more than happy to try to incorporate your feedback if it is helpful to the course. So definitely go fill those course evaluations out. and I will talk to you guys next week.